Yo, what's up, SUPA peeps? Today we are doing the last lecture on Unit 3. And it's dealing with the topic that I'm sure none of you have ever talked about. So we're talking about what's called molecular orbital theory. And the projector's not acting right. I guess we'll deal with it. All right, so this is molecular orbital theory. It's Mo theory for short. It's not even on the screen. What's going on here? Why is this giving us trouble? Okay, that's a little better. So, molecular orbital theory. It's used to understand the magnetic properties of molecules. I'm going to be honest, molecular orbital theory is wacky. This is some stuff that's far out, and it's pretty hard. So we're really just going to hit real basics of molecular orbital theory. Excuse me. So we've talked about orbits before and orbitals. Let's label this A. So when we're talking about individual atoms, they have what are called atomic orbitals. Okay, it's those areas of space where got a frog in my throat, where we will probably find electrons. Okay, so what we're really talking about here with these atomic orbitals, those are our S, P, D, F, and even our hybrid orbitals. And we spent a lot of time with these, so we know the S orbitals are sphere-shaped, P's have that dumbbell, our D's are four-leaf clovers, and so forth. So we spent time looking at these. So this is when we have individual atoms and what their electron orbitals look like. Maybe I have COVID. Ugh. More coffee. All right. So when atoms come together, they form molecular orbitals. So remember, when two atoms bond and come together, their orbitals overlap. That overlap forms molecular orbitals. So there's some things here we got to talk about. So just like atomic orbitals, ooh, this pen is dead. Just like atomic orbitals, molecular orbitals each have a specific amount of energy. Okay, so just like the S has less than the P, and the P has less than the D, and so on and so forth, we have the same thing that happens in molecular orbitals. Just like our atomic orbitals, each molecular or Mo orbital can only have 2 electrons, and they have to have opposite spin. No, this should be 3. So when atoms bond, the atomic orbitals overlap. And combine to form 2 types of molecular orbitals. First type are what are called bonding molecular orbitals. When you have when bonding molecular orbitals form, these have a lower amount of energy than the atomic orbitals of each atom. Now, so let's talk about this. So when we were talking about bonding, remember we talked about sigma and pi bonds? Well, when we're talking about sigma and pi bonds, we're really talking about the beginning of molecular orbital theory. So if you remember, let's look at hydrogen again. Okay, if we have 2 hydrogens or s orbitals, these are going to overlap. Okay. And we end up getting really something like this. Okay, and then the internuclear axis is here. And we said that this is a sigma bond. Well, this overlap is what we're talking about with bonding molecular orbitals. Okay, because when these 2 s orbitals combine, the orbital shape actually changes. And for every 2 orbitals that overlap, we get 2 molecular orbitals. So let's write that. For every 2 atomic orbitals, that overlap, we produce 2 molecular orbitals. So in this case, okay, when we overlap 2 s orbitals, or an s and a p, when they're on the internuclear axis, okay, we get what's called a sigma bond. How do I want to do this? Let's do it this way. So this overlap, okay, this sigma bond produces 2 molecular orbitals. One of them, okay, here, these are my nuclei. One of them looks just like this. And this is called the sigma M molecular orbital, the sigma molecular orbital. Now, remember, all of these orbitals are based on wave mechanics and waves. Okay? And waves can have constructive interference and destructive interference. And that's all from physics. And what this is showing with our sigma bond, or our sigma molecular orbital theory, this is constructive interference. So this is our electron density, and we're going to probably find electrons all through here. Okay. Now, the other bond that forms is what's called an anti-bonding molecular orbital. And let's do this. Let's put B here. Let's write anti-bonding molecular orbital. So we have bonding molecular orbitals and anti-bonding molecular orbitals. Our anti-bonding molecular orbitals have a higher amount of energy than the atomic orbitals of each atom. So the anti-bonding of a sigma bond, okay, is called an anti-sigma bond. All right. So the other thing that happens when we take this 2s orbitals and overlap them, right? We get something like this. Here are my 2 nuclei. But we have this, something like this. And there's a nodal plane in here. Okay. So this is called the anti-sigma bond. Okay. Anti-bonding sigma bond. And we show that it's anti-bonding by putting a star here next to the sigma. Okay, so 2 orbitals are formed when we overlap and form a pi bond. We get a sigma bond. We get a sigma MO, which looks like this, and we get an anti-sigma that looks like this. All right, what about P's? Well, remember, our P's, or P orbitals overlap, and I'll put here. Remember, we got that pi bond, so there was an area above and below the internuclear axis. This was a pi bond. Well, this is what's actually called the bonding pi molecular orbital. All right, so this is the actual shape of our pi molecular orbital. But remember, for every 2 atomic orbitals, we produce 2 molecular orbitals. Okay, so one of them looks like this. This is the bonding molecular, pi bonding molecular orbital. What does the anti-bonding molecular orbital, pi, look like? Well, it looks like, okay, so if we have our nuclei, it kind of looks like and there's a nodal plane here. This would be my pi anti-bonding orbital. It's what it looks like. Okay. Now, the bonding molecular orbitals, okay, are formed because of constructive interference. Okay, and we get this, okay, what makes sense, I think. Okay, these orbitals that bond these together. Our anti-bonding are produced by destructive interference, all right, which means there's areas in here that are canceled out by the wave theory. And we don't find electrons in here where we normally would think during a bond. That's why these have much higher energy than these. Okay? And I want to show you, because this was messy, so let me show you something from the textbook. So in this first thing, we're adding a PZ, 2 PZs together. And you notice that they're going to be side by side. Okay, so this is going to end up being a sigma bond. Now remember, we get, for each atomic orbital, we get 2 bonding orbitals. Okay, this is one of them. This is my sigma 2p bonding orbital, molecular orbital. And you can see where, look, this is where that overlap's occurring. All right, here's my nucleus, here's my nucleus. This is my anti-bonding sigma orbital. You got that nodal plane, right? And we end up getting, okay, more electrons out here. This has much less energy than this guy. Now, this is going to be our pi bonds. Okay. So you notice here's a 2px and a 2px. They're parallel to each other. Here are my nuclei. When they overlap, they form 2 molecular orbitals. They form a bonding pi orbital and an anti-bonding pi orbital. Okay, this is where, okay, we would expect those electrons to be above and below that internuclear axis, but it also produces this weird anti-bonding with this node in between. Right? This is the same thing, except it's just in a different plane. This is the py instead of the px, but it's doing the same thing. Okay? Hopefully you kind of get an idea of what these orbitals look like. Okay, now what we're going to do is we're going to take these orbitals and we're going to fill them with electrons just like we filled them when we were dealing with the atomic orbitals. All right. I think that was all 3. So let's label this 4. We can figure out bond order using molecular orbital theory. Now remember what our bond order tells us, all right? Strength of the bond increases with bonding order. Come on. In this case, it's going to be a little bit different to calculate when we're using molecular orbital theory. Our bonding order is equal to the number of bonding electrons minus the number of anti-bonding electrons, all divided by 2. Now, in general, if there are more bonding electrons than anti-bonding electrons, the bond is stable. All right, so let's get into this. We're only going to deal with very, very, very simple molecules. So we will only be using molecular orbital theory with homonuclear molecules. Okay, homo means same, all right? So these are same atoms. All right, do I have enough room here? I don't think I do, so I'm going to flip this. So we're going to start with group 1 and group 2 atoms. And in group 1 and group 2, so any one of group 1 and group 2, okay, if they bond, what we're doing is we're combining s orbitals only. They don't have any p orbitals. So what we're going to do is we're going to draw something like this. Okay, so this is one of the atomic s orbitals. This is the other atom's s orbital. I'm going to draw a little dotted line, little dotted line, little dotted line, little dotted line. I'm going to put a line here. I'm going to put a line here. Now, these two s orbitals are going to overlap. And we get 2 molecular orbitals. Do you remember which molecular orbital has less energy? Well, the sigma bonding one has less energy than the sigma anti-bonding. Okay, so in reality, just like when we were doing diagrams with the atomic orbitals, okay, this is an increasing energy. Okay, so this has less energy than this guy. All right, so this is just a general chart that we're using. All right, so this is going to be for one atom. This one is the other atom that we're bonding. And then this represents our molecule. Now remember what we said. The sigma s molecular orbital will have less than the atomic orbital. The anti-sigma will have more. Right? Now, this is the chart that we're going to use when we're ever bonding a group 1 or group 2 atom. Right? So let's try it. Okay, let's try and see what we're going to do here. So we're going to start simple. Let's start with diatomic hydrogen. And the first thing you have to figure out is total electrons. No, total valence electrons, sorry. And in this case, there are 2. 1 from each hydrogen. Okay. Well, what I want you to do is I want you to draw this chart. Okay, so we have the 1s orbital from the first hydrogen. We have the 1s orbital from the second hydrogen. These two are going to overlap. We're going to get 2 molecular orbitals. We're going to get a sigma 1s molecular orbital, and we're going to get a anti-sigma 1s orbital. Okay, so we get the sigma 1s orbital. There's my bonding orbital. This is my anti-sigma 1s orbital. Now, okay, let's go ahead and fill in what the atomic orbital would look like. Well, we have 1 electron, so it would be an up. We have 1 electron over here, so it would be an up. Now, when these combine, they want to go into the lowest orbital, right? So we're going to combine this. This guy's going to come down here. This guy's going to go down here. So in hydrogen, this anti-bonding orbital is empty. We are only filling this bonding molecular orbital. Now, this has what's called a molecular electron configuration. And the molecular electron configuration for diatomic hydrogen would be sigma 1s2. Okay, so we're in the bonding sigma orbital, first principal energy level, okay, s, okay, and there are two electrons in that orbital. So this would be the molecular electron configuration of H2. Now, just for fun, let's calculate bonding order. Our bonding order equals number of bonding electrons minus anti-bonding electrons divided by 2. Well, there are 2 bonding. There are 0 anti-bonding divided by 2, and we end up with 1. Okay, which is what we did before. It's actually what we found before. And it better be. Because we know that there is a single bond between 2 hydrogen atoms. Now, you just have to memorize this pattern for groups 1 and 2. You got to memorize it. I'm telling you right now. Okay, if you memorize that for groups 1 and 2, you're good to go. Now let's try Let's try Li2. Okay. Can lithium be diatomic? Right. Well, it's in group 1. So as soon as you see that it's in group 1, all right, we can draw that same chart. Right, except lithium's valence electrons are in the second principal energy level. So this is in the 2s orbital. Right? And it's again it's a group 1, so it's going to be an up-up. So this is going to be the sigma 2s. This is going to be the anti-sigma 2s. So when these lithium atoms overlap, we're going to get an up and a down. So its molecular electron configuration would be sigma 2s2. I would probably write it this way, sigma 2s2. I would probably do it that way, right? That shows you that all of these go together. So let's not do it that way. Let's put the number of electrons outside the parentheses. Now, what would the bond order of this be? Well, bond order equals our number of bonding minus number of anti-bonding divided by 2. We have 2 bonding, 0 anti-bonding divided by 2, right, which would give us 1. All right, so if this was to occur, it would form a single bond. All right, let's try helium, diatomic helium. Now, I know it's over there in group 18, but it acts like a group 2. Okay. So let's just see what happens here. This has 4 total valence electrons. This is my 1s. This is my 1s. So this is 1 helium atom. This is my other helium atom. It would be up down here and up down here. This would be my sigma 1s. This would be my anti-sigma 1s. Now, one of these is going to come down here. One of these is going to come down here. Okay, so we did this one and we did this one, and then this one, and then this one. So the molecular electron configuration would be sigma 1s2 anti-sigma 1s2. So that would be my molecular configuration. Okay, now, just for fun, let's look at bond order. We have 2 bonding. We have 2 anti-bonding divided by 2. 2 minus 2 is 0, divided by 2 is 0. What is that telling me? It's not stable. It will not happen. Will diatomic helium form? The answer is no. Okay, it's not stable. So that's what this bond order is telling us. All right. So this is the thing that we're going to use. This is the diagram that we're going to use for groups 1 and 2. Well, as soon as we get over into group 13, 14, 15, 16, 17, now we're dealing with p orbitals. All right, so that means we're going to get into pi bonds and anti-pi bonds. Okay, so they become a little bit more complicated. So now, let's start down here. We still have, okay, we're still going to have s orbitals overlapping. We're still going to have this. Okay, and this will be a 2s, and this will be a 2s, and it'll produce a sigma 2s and an anti-sigma 2s. Okay, so those are for my s orbitals, but then we have our 3 p orbitals. Okay, so these are my 2px, 2py, 2pz. These are my 2p's. If we have 6 orbitals overlapping, or 6 orbitals coming together, that means we're going to have 6 molecular orbitals. And this is the order of energy. I don't know why we put these dotted lines here. I don't know. You don't really need them. Now, what are these molecular orbitals? This is the pi 2p orbital. This is a pi 2p orbital. This is a sigma 2p orbital. This is a pi, an anti-pi 2p. This is an anti-pi 2p. And this is a anti-sigma 2p. Okay, and remember, this is from low to high energy. So when we go to fill these molecular orbitals, we're going to start down here and work our way up. Okay, now, in reality, I don't write it like this. Okay, so when I go to fill mine in, and you're going to be able to eventually do the same thing, instead of writing it this way, this is how I write it. I just go, okay, I know what I got to do. I got to 1, 2, and then I go here and here, and then I go here, and then I go here and here, and then I go here, and then I go back and label them. This is my sigma 2s. This is my anti-sigma 2s. This is my pi 2p, pi 2p. This is sigma 2p. This is anti-pi 2p. This is anti-pi 2p, and then this is sigma 2p, anti-sigma 2p. Right? This is the same thing as this. Okay. Eventually, you're going to get to this. Right? Now, you have to memorize this pattern. You got to memorize this. This is for group 13, 14, and 15. These are the molecular orbitals in their correct energy states. Okay. So let's go ahead and use it. So let's do group 13. Let's do boron, B2. All right. If we look at boron, its valence electrons are 2s2, 2p1. Okay, so we have 3 valence electrons for boron. So we have a total of 6 valence electrons in the molecule. All right. So this is group 13. So the first thing I'm going to do is I'm going to draw my 13 chart, my group 13 chart. All right. So, and I'll do it this way. 2s, 2s. This is my sigma 2s. This is my anti-sigma 2s. Put dotted lines in there if you wanted. These are my 2p's. And we go and then and this is my pi 2p, my pi 2p. This is my sigma 2p. This is my anti-pi 2p, my anti-pi 2p, and my anti-sigma 2p. And again, we could put dotted lines in here. Whatever, I don't really usually put those in, but okay. All right, now we're doing boron. All right, so boron, we just did 2s2, 2p1. So it's up, down, up, down, up. So now we're going to start filling, and we fill from low to high. Okay, so here we go. Ready? Okay, we take one from here, change color. One from here, put it there. One from here, put it there. So we've used 1, 1, then we go up, down. That takes care of this guy. All right, now I have one from here. It's going to go here. Now, just like we fill these one at a time before we pair, it's going to be the same thing with these guys. So before we pair this guy up, we put one over here. So it goes like that. All right. This, okay, is the diagram for boron. Now, what's my molecular electron configuration? Well, we would go sigma 2s2, anti-sigma 2s2, and then pi 2p2. That would be my molecular orbital electron configuration. Now, let's do bond order. We have our bonding electrons. This is a bonding, and these are bonding, so it's 4 minus our anti-bonding, 2 divided by 2, and that gives us 1. Okay, we would form single bonds there. As long as you know this pattern, it's easy to figure out. Now, we're going to use this for something else in a little bit. Okay, we're going to use this for something else in a little bit. Let's try another one. Let's do P2. Okay, so this is a group 15. Okay. And its phosphorus valence electrons is 3s2, 3p3. So each one of these has 5, so we would have total valence electrons equal to 10. Now, since it's a group 15, we can just go ahead and draw in our orbitals, okay? And I'm going to just do it the way that I usually do it. Sigma 3s, anti-sigma 3s, pi 3p, pi 3p, sigma 3p, anti-pi 3p, anti-pi 3p, and sigma pi, anti-sigma 3p. Okay, so this, again, it's that pattern for group 13, 14, and 15. All right, now we have to place 10 electrons in here. We started at the bottom and worked from the top. 1, 2, 3, 4, 5, 6, and then we can pair up 7, 8, 9, 10. Now, we can go ahead and get my electron configuration. Okay, it would be sigma 3s2, anti-sigma 3s2, pi 3p4, and sigma 3p2. All right. Let's do bond order. So it's the number of bonding minus number of anti-bonding divided by 2. All right, so we got 1, 2, 3, 4, 5, 6, 7, 8 bonding, 2 anti-bonding divided by 2. 8 minus 2 is 6, divided by 2 is 3. What's that telling me? It's a triple bond. Now, this is for P2. Just for fun, I'm going to change colors. What would happen to this if I did this to you? P2 with a -1 charge. So now, instead of 10 valence electrons, now we have 11 valence electrons. What would that do to this guy up here? Well, it gives us an extra electron. So where would it go? It would go right here. And now my electron configuration would be sigma 3s2, anti-sigma 3s2, pi 3p4, sigma 3p2, anti-pi 3p1. Okay, we could do the same thing with this. Instead of P2 minus 1, what if I said, hey, what is the electron configuration for P2 plus 1? Well, we would go back to our original, and we'd be missing one of them. Okay, so we would lose this one. So instead of this electron configuration, it would be the same thing, except it would be sigma 3p1. So you could play with ions. You just start with the base, all right, and then either add or subtract electrons as you go. Okay, so this is the order that we use for groups 13, 14, 15. Well, what about 16 and 17? Well, its molecular orbitals are different also. So this is the pattern that we're going to have for group 16 and 17. Sigma 2s, anti-sigma 2s, and remember this is for my 2s orbitals. Okay, so this would be the 2s. Then we get sigma 2p, pi 2p, then we get anti-pi 2p, and then we get anti-sigma 2p. So these are my p orbitals, this is my s orbitals. So now, again, you have to memorize this pattern. If you memorize the pattern, it's pretty simple. So let's do diatomic oxygen. Two S2, 2p4. Okay, so it's got 6 electrons, so we're going to have a total of 12 valence electrons to place into this. All right, so let's draw the chart out real quick. sigma 2p, anti-sigma 2p, these are S's, sorry, oops. This is sigma 2p, so we got sigma 2s, anti-sigma 2s, sigma 2p, pi 2p, pi 2p, anti-pi 2p, anti-pi 2p, and then sigma, anti-sigma 2p. All right, we got 12. 6 from each. So here we go. Start at the bottom, work our way up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. Electron configuration would be sigma 2s2, anti-sigma 2s2, sigma 2p 2, pi 2p 4, anti-pi 2p 2. So that would be my molecular. Okay. This is what happens when we overlap them and form diatomic oxygen. Bond order. Well, how many bonding do we have? 2, 4, 6, 8. Antibonding. 2, 1, 2, 3, 4. Divided by 2, which gives us 2. Double bond. We know diatomic oxygen has that double bond, so it works out pretty well. All right, let's try another one. Let's do diatomic chlorine. In its valence shell, we got 3s2, 3p5. So we're doing with a third principal energy level. We're going to have 14 valence electrons to play with. All right, well, we do the same exact chart. This would be my sigma 3s, my anti-sigma 3s. This is my sigma 3p. This would be my pi 3p and my pi 3p, anti-pi 3p, anti-pi 3p, and my anti-sigma 3p. Now we just have to fill them in. We got 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. All right, so we would get sigma 3s2, anti-sigma 3s2, sigma 3p2, pi 3p4, and anti-pi 3p4. Bond order. We have 8 bonding. We have 6 anti-bonding divided by 2 equals 1. So we form a single bond. All right. So we'll never have to deal with the transition elements. So you just have to be able to deal with groups 1 and 2, groups 13, 14, and 15, and then groups 16 and 17. All right. Each one has its own pattern, and you got to memorize them. 1 and 2 is easy. These are the ones that you have to keep separate. We need to use this for something else. Okay. This is used to figure out the magnetic properties of these different molecules. Okay, so they all have different magnetic properties. Now, the spin of an electron produces a small electric field, small magnetic field, let's say that. So if you have a charge that's spinning, it gives us a magnetic field, right? And those spinning electrons produce two different things. We can get paramagnetism. And that's one word, paramagnetism. This is a type of induced magnetism associated with unpaired electrons that causes a substance to be attracted to the magnetic field. The more unpaired electrons, the stronger the paramagnetism. So what we're going to be looking at is we're going to go back to our molecular orbitals, and we're going to be looking at the electrons. Are they unpaired or are they paired? Because if they're paired, that's called dimagnetism. So dimagnetism is a type of magnetism associated with paired electrons. This causes a substance to be repelled from a magnetic field. Now, why does that happen? Well, remember, if they're paired, we have two electrons. Okay, so we have two electrons if they're paired. One of them is spinning this way. The other one is spinning this way. They have to have opposite spin. If those two electrons have opposite spin, the magnetic field each produces is canceled out. So if it's by itself, if the electron's by itself, it's producing a magnetic field, and that magnetic field will be attracted to another magnetic field if we put it into it. But if I have two of them, each one is producing an opposite magnetic field, so they cancel each other out, so they won't be attracted to a different magnetic field. Okay? So paramagnetism is when we have one, di is when we have two. Now, before we go back and look at some things, I just want to write one more thing. Paramagnetism is much stronger than dimagnetism. Okay. Para is stronger than di. Because of that, so any substance that has both paired and unpaired electrons will exhibit a net paramagnetism. In other words, if you find unpaired electrons, it's going to be para. Okay. If they're all paired, it's going to be di. Okay, so let's go back and look at some. Nothing here. All right, so let's look at diatomic hydrogen. If we look at that diatomic hydrogen, the electrons are all paired. So that means this would exhibit dimagnetism. In other words, if I put hydrogen in an electric field, okay, if I put this in an electric field, it'll be repelled from that field because it's only paired. All right. Let's look at lithium. Again, only paired. Okay, it only is paired, so this would exhibit dimagnetism. It would be repelled in that magnetic field. Let's look at helium. Paired. They're all canceling each other out. This would be dimagnetism. Again, it would repel in a magnetic field. Let's look at this phosphorus. Now, remember we added that. Paired, all paired. This would be di. Now, if it happened to be an ion, then we have an unpaired. Okay. In this one, it's unpaired. As soon as you have unpaired, it becomes para. Okay, so the ion itself would be para, but the atom molecule would be di. All right. Boron. Okay. Paired, look here. Unpaired. These are unpaired electrons. So this would be para. Okay, this would be attracted to the magnetic field. What else we got here? Oxygen, diatomic oxygen. We have unpaired. This would be para. Okay, it would be attracted to that magnetic field. Chlorine, paired. Everything paired. This would be dimagnetism. It would be repelled. So we need to use these molecular orbitals to figure out their magnetic properties. Okay. If they're paired, they're di. Right? If you have any unpaired, it's para. Now remember, the more unpaired there are, the stronger the para it is. All right. So that's the end of the unit. you're going to be working through some of this stuff. All right. And I will talk to you soon.